Major question for today. We're talking about material selection. We actually began a little bit on Monday. How can life cycle environmental considerations be factored into material selection? So we'll be talking about material selection. But it really is hard to find examples where you can just isolate the material and the material production from the life cycle. And that's going to be very obvious and probably the big lesson from today. Talk about the relationship to the lids wheel and some nuances here. Went through the lids selection strategy here, what we're really trying to do when we select materials. We, of course, want to consider the mining and processing, the quantities of the material we're using, how much toxicity went into the production of the material, and the manufacturing process for that material. Transportation impacts we'll talk about. In-use pollution we've talked a lot about. We'll have one more example today with fuel tanks, maximizing lifetime, and end-of-life impact, as we said, Friday and Monday. We'll talk much more about those. Some of our examples, we went back to the seed phone already, the radiator grill now 4 or 5 times this term. We'll really begin in earnest with the diaper example, milk packaging and manifolds, and we're going to contrast the different lessons here. Mining and processing impacts, we'll talk about steel versus aluminum versus ABS plastic, and really quickly go through paper versus plastic on the grocery bag side, at least from the production standpoint. Fuel efficiency and material quantity, right? You're moving the product, that becomes quite important. Manufacturing, we'll give a whole lecture to on Friday. Transportation impact, we'll look at Eco Indicator 99 metrics for air versus truck versus sea versus rail. Again, use this fuel tank material example. Look at a plastic fuel tank versus a steel fuel tank and show basically the life cycle impacts of that selection. Okay, so this is a familiar example. Won't go through it again. It just basically demonstrates that material selection is not just about the material selection. It's about the life cycle. And that shows up also in the cell phone example where we showed that manufacturing, and we'll go through these data again, showing that manufacturing is relatively more important. We talk about these handheld consumer electronics devices. So if we undergo efforts, as we did, to remanufacture this product inside of a new housing, it's not just about design for disassembly, right? That'll get you part of the way there, but the aesthetics matter. And although the majority of the environmental impact is in that manufacturing stage, you really can't diffuse the product delivery system into practice without some type of a carrot, either a fancy housing, right, such as this one, or something catchy like the idea of the seed phone. And even though the housing really doesn't matter from the standpoint of total environmental impact, we talk about cell phone manufacturing, the housing's less than 1% of that impact if we talk about energy in particular. But nevertheless, it is waste. So if we have the opportunity to do something clever, maybe we could. And hopefully someday we'll actually try to prototype one of these. Okay, we got into the diaper example. This was the point really to demonstrate that the consequences and habits that are implied by material selection may be more important than the material selection itself. The key ideas here, not just the functional unit idea, but the functional unit. So we're talking about the material we might select, the assumptions that go into how we use the product, and equivalent use. And especially in this example, it's a trade-off. Got a question here?
Yeah. Do you see this as a decision that the design team in a company would consider?
No.
Okay. Because they seem like very different markets.
Yeah, of course. And if you're in the business of making plastics and delivering plastics products, and you've got packaging lines that you're invested in to deliver disposable diapers, you probably wouldn't think about cloth. All right? But this is a case where we're just demonstrating that the life cycle implications, right? If you're making plastic diapers as a designer, you should still think about out-of-the-box alternatives, right? And the use patterns that are set into motion. So that's the point here. You probably wouldn't be necessarily deciding between such diverse options. You're probably in the market for one reason or the other. You do plastic, disposable products. You've got certain packaging skills, value added, that you're bringing to bear. But that doesn't mean that necessarily what you're making is the best for the environment, right? So it's more of an illustrative case study than anything else. And the same probably goes for milk packaging, too. Let's come back to that at the end, because this is a very important point. And what assumptions might you make, right? Here you are replete in all sorts of different assumptions, right? How many diapers are you going to use, right? There would be a certain ratio one might expect. And this was an investigation, as we talked about on Monday, about 10 years old now. But you might have alternative use for these cloth diapers. And they estimated a ratio of cloth to plastic diaper use of 1.6 to 1.9. It's almost 2 to 1. The lifespan, how long does it last? I mean, this is very illustrative, whether you're talking about design and manufacturing example or a personal choice at home. It doesn't matter. These assumptions are going to be there. You're going to have to make sometimes stab-in-the-dark types of estimations, right? So the point here is to bring one home that is very easy to understand and show how really these assumptions play into the conclusions. How long would a cloth diaper last? Well, they assume 180 uses before it's disposed of as a rag, and that rag would have certain use time also. The market share. Are you laundering these cloth diapers at home, or are you having a service do them? That would make a big difference, as we'll see. Laundry loads, assume 3 loads of cloth diapers, even the temperature of the water that one might use. They assumed 60 degrees Celsius on the wash, and the rinse was 30 degrees Celsius. What percentage of dryer drying versus clothesline drying? They assume 68% to 32%. I don't recall ever seeing a laundry line in the United States. Maybe I have, but I can't think of a time when I actually noticed one. Well, they assume 68% to 32%. I think that's probably skewed. Energy consumption. Okay, if we go through the functional unit of servicing a baby per week, here is the energy consumption. 150 megajoules per baby per week in the disposable diaper realm versus closer to 200, maybe 190 on the home laundered cloth versus something around 140 to the cloth service laundered. Do these look like significant differences, given the uncertainty in the assumptions? A lot of people shaking their head no. I would probably agree. Water usage, however, and if you look at the y-axis here, you see a much bigger scale, 0 to 1,000 liters per baby per week. Here you see much bigger differences, almost factor 2 or beyond between disposable and the cloth home laundered, right? Disposable diapers are bad, right? Well, what if you care about water pollution? Certainly not, right, in this case. The service laundered, due to the economy of scale, these are not dry laundered, or dry cleaned, I should say. But this is an efficiency that comes from many more cloth diapers in the same batch being washed. Question?
End of life then in terms of your laundered cloth diapers are going to wastewater treatment facilities, whereas your disposable diapers are going to landfills. And then can you start to look into that level and say, well, which are we handling better, the wastewater treatment or landfills?
Well, you got to let me finish, because we're going to mention this. Right. Of course, I mean, we have to, right? But you're going to have to draw the boundary somewhere. Okay. For instance, back when these data were produced, to my knowledge, there was not a good life cycle assessment of a wastewater treatment plant, at least here in the United States. Would those data have been included here? I doubt it. So they probably drew the boundary very tightly around the drain in the house, right? But you bring up excellent points, and we'll come back to solid waste here. But which categories you pick, and that's really what your question's applying, says a lot. I mean, I think I mentioned the book before, right? How to Lie with Statistics. I really should remember the author, but you could do a lot to really skew or make a case for whatever it is you want to say. So one would have to conclude here, based on data that is now available for a wastewater treatment plant that actually we have available to us. We'll talk a little bit about wastewater treatment on Friday when we talk about metalworking fluids and metalworking fluid disposal. That data are available. So, would one be motivated, or should one go and check those data out? Remains to be seen, but we could go in and look at the data and say yes or no. Right? And here you have a lot of averaging, right? The wastewater from my house or your house is all lumped together, right? Or from the University of Michigan, for that matter, or even domestic uses in industrial facilities. These are all lumped together. So it gets very hard to kind of separate these things out into meaningful point of use decisions. Right? So you point out some of the nuances that are not captured here. Airborne emissions would be another thing we should include. Here, again, you see this compressed scale from 0 to 0.2 kilograms per baby per week. Are these differences likely to be significant? Probably not. They all look pretty much the same, and certainly within error on the assumptions. But talk about raw materials. Disposable diapers, of course, use much more raw materials, upwards of 6 kilograms per baby per week versus 2 on the cloth. And, of course, solid waste is going to follow directly, not just from the diapers, but also from the packaging. Okay. And you see a little bit more solid waste from the service laundered diapers. That's probably from packaging on the redelivery when they're brought back. Okay, so if we were to summarize, right, the differences between cloth and disposables are significant with respect to water and waterborne wastes, and with respect to materials and solid wastes, where the cloth consumes more water, produces more aqueous waste, and the disposables consume more raw materials and make more solid waste. The materials are obviously important, but here it's really the life cycle, right? It's about how they're being used, right? Certainly if you could reuse a plastic diaper 160-odd times, or whatever the number was, right, that number would be way down. It really highlights the fact that the life cycle is important. And we have to be honest, when energy, air emissions, and other emissions in these material selection examples are too close to call, we have to call them exactly that. And where things are not included, such as impacts at the wastewater treatment plant, that also should be noted. All right? So too sensitive, and that's the last bullet point here, right, to reasonable variations in use ratio, market share of home versus service laundry. This issue of clothesline drying and water temperature really will drive these decisions. Okay, so we're too close to call, and this really is it boils down to, in the absence of any prioritization that we make as a society, this becomes a personal choice. And again, I mentioned I don't have any kids, but I care more about water than I care about solid waste. That's just a personal preference. Landfill space around here versus waterborne waste. Certain things are a lot easier to reverse than others, and we're talking about pollution. And that's just my own view on it, and it's not right or wrong. But we do need at some point to get together and make some priorities and decide as a society what we should be, especially with respect to specific industries, what these environmental priorities are. And that's going to be the topic of our last roundtable, coming up in, well, now about 3 weeks. Now, even for materials that are used exactly the same, this is why I picked the example of milk packaging. Here is something where you might be in the business of producing and delivering milk, and you might have some control over which form of packaging you choose. You might not, depending on how the supply chain is set up. But here's a hard-to-find example where the materials are used in exactly the same way. So we'll consider milk packaging, glass, high-density polyethylene, linear low-density polyethylene flexible pouches, polycarbonate, and paperboard. Some of these can be reused, the glass, the high-density polyethylene, and the polycarbonate, but that also affects the design. So you need a more sturdy design so that the reuse, it can basically the milk packaging can withstand cleaning, transportation, and multiple uses without breaking or becoming damaged. Materials have inherently different energy and solid waste performance or emissions. And we could talk about cost and performance. As much as we can say that, a plastic container is the same as a glass container because they both deliver a gallon of milk, the fact is they are different. So even where we're trying to find an example where the materials may imply exactly the same in-use characteristics, it's almost impossible to find that. Right? So again, we've got to be thinking life cycle. Our functional unit here will be 1,000 gallons of milk delivered. Here are just the raw materials for the different containers that were investigated in this study. Looking at grams per container here, both half-gallon and 1-gallon containers. We've got basically the 1 gallon here in red and the half-gallon in blue. And you see here straight away the raw material use to bring to market a glass container. We're almost at 1 kilogram for the half-gallon and about 1.5 kilograms for the 1 gallon. All right, that's for the refillable one. It needs to be a stronger design to avoid breakage in the refilling and reuse. Glass at the one-time use is the next highest category, and we're down a factor of 5 below. We start getting into the high-density polyethylene refillables and one-time use. You see that these bars are very small. We talk about raw material use per container, where the linear low-density polyethylene pouch is hardly even showing up here. So that'll be our first category. Just to give you a sense of the market here, this is milk container material. On the left-hand side, this is the percentage of the United States market. You see somewhere around 60% high-density polyethylene with a balance made up of paper containers. Okay. And it's hard to talk about this without talking about the end-of-life system. All right, here's the glass market. Over here, you see that the value of glass over a 2-year period, 2.5-year period, is roughly constant, right? And that's going to affect your end-of-life supply chain, right, your recyclability. Whereas at the top here, high-density polyethylene is spikes and valleys of recycled material cost. Here is a factor of 3. Okay. Interesting to note that while our market is contained almost completely of high-density polyethylene and paperboard, in Canada, flexible pouches are about 83% of the market, or at least were 10 years ago. Okay, so it's an interesting distinction to make. Mark?
What exactly is a flexible pouch?
What's that?
What exactly is a flexible pouch for milk?
I think we have an answer here.
Living in Canada, you actually go to the grocery store and you'll see they'll have 2 half-gallon pouches, and then they'll have a wrap over it. And so they have a little, like a pitcher that you can buy at the store. You put the plastic bag into the pitcher, and you cut one part of the plastic bag, and when you pour the milk in your glass, and then you kind of take a little paper clip or something and top the back off and leave it in the refrigerator.
How many people in the room would prefer that product delivery system? We got one.
Oh, I'm used to that.
I like the Tetra Paks.
The what?
Tetra Paks,
Tetra Paks.
They're a European thing. They're like a box.
Oh, yeah, the little box.
Yeah. Those are my favorite.
Me too.
Yeah.
All right, but rare to find around here. Okay. Well, a few people are used to it, right?
It's cheaper. It's cheaper to buy it's called sachet, I think it's called.
I don't know the name of it.
It's called sachet, right? It's cheaper to buy that than buying it into cardboard or glass or
Interesting.
whatever.
So where is it cheaper to buy?
Oh, in Argentina at least.
In Argentina, okay.
But since we use the metric system and not the gallon system, like you wouldn't go and find a bottle for 3.89 liters, 1 liter or half liters. That's how we buy milk.
I got actually a cost plot at the end of this, and yes, it turns out to be cheaper. Here, it doesn't factor into the cost, or at least people don't notice it or don't care to notice it. And that's an important conclusion, right? And so it's hard to separate out the market performance here when we talk about these issues. And again, I think it helps to bring an example home, right, to see what some of the characteristics are. At least for these examples, if we talk about energy use, in megajoules per 1,000 gallons of milk delivered, here glass is king. Of course, this would be a case where you don't want to be king, but about 15,000 megajoules to deliver 1,000 gallons of milk. This is the one-time glass container. Now, even with 5, 20, 30 trips, still the energy consumed, and oh, by the way, sorry, I should have gone through these. The blue is material production energy. The red is total life cycle energy. Okay, that's for the half-gallon container. And then for the 1-gallon containers that you're comparing against, yellow is material, and the turquoise is 1 gallon. Okay, so what do we learn? Just looking at glass, what we see here, it's quite obvious that if you have more trips and more uses, the energy use to deliver 1,000 gallons of milk is going to go down. And that is because the material production is so energy consuming, and that's indicated here by the one-time use. Even though the design is a little bit less rigid, let's say, it will only be more energy consumption for one-time use of a refillable bottle, right? More material. Okay. So that's the first thing that we see here. The second thing we see, that as the number of trips increases, the percentage of energy consumed by the material production goes down. Right? So more energy is empty container, trips, and refilling and cleaning energy. Right. And we also see, as we compare 1-gallon delivery system to half-gallon delivery system, that the energy actually goes up as you go to the half-gallon. Okay? Which makes sense. More material to deliver the same product. Okay? But again, you're barely seeing even 30 trips on glass versus the linear low-density polyethylene approach. Okay. Now, by the way, in the life cycle, as it was mentioned here, all the steps that were mentioned were included in the life cycle, such as the container that you'd need to keep it in, how many uses for that container, rinsing that container out, and I think they had a variety of clips, and I don't remember exactly what those were, but those were included too. So they did consider the whole system, or at least an example system. Okay, high-density polyethylene, the majority, the one-time use here. Just a comparative perspective, here's the, I don't know, we don't buy much milk. I think it's 1 gallon is the common one, the most common. Maybe not. Maybe it's most common in our house. Actually, we started buying that soy milk, so I haven't seen regular milk in our house for a couple of years now. But anyway, not too much difference, but still a lot more than the linear low-density polyethylene. A paperboard shows up here, and you see that the plastic half-gallon is a little bit more energy consuming than the paperboard, but not too much. Question?
50 trips, do you mean to the recycling center and then getting turned back into another bottle and then going...
No, this is refilling. Reuse, not recycling.
Do they reuse milk bottles?
Not here. But they can be done. Remember, milk used to be done this way. Used to have
glass,
milk delivered,
right?
Yeah, for glass. Right? But conceivably, it's possible to do with polycarbonate too, and it's lighter. But there wasn't an actual example of this, to my knowledge. This was an estimated for polycarbonate. Good question. Okay, so basically we've been through this. More trips, larger bottles, right? Reduce the energy per service. Solid waste, no surprise at all. Glass, because there's a lot more material there, there's a lot more to waste. Now, consumers would tend to think that glass is more recyclable. It is recycled to a fairly high rate, about 20%. But when you factor that 20% in, it doesn't put a dent on the relative comparison with solid waste by these other product delivery systems. Okay, and even to compare them, we have to take that glass out of the picture. So I just removed it here on this plot. And now we've got the 5-trip glass here defining the y-axis, so we can compare some of these others. Right? So it's a very important point. You know, recyclability, you have to look at, first of all, how much material is being used in the first place, and the second, how much of that material is actually expected to be recycled in the first place. Right? Okay, so here is our high-density polyethylene single use. Okay, sorry. And here is our paperboard. So the high-density polyethylene half gallon, uses less material in terms of solid waste, I should say, than the paperboard, but it also has, the paperboard uses more material, but if we look on the previous graph here, the paperboard also uses a little bit more energy, right? Do I have that right? No, I don't. Here's a comparison. High-density polyethylene on the total life cycle in red, more energy than paperboard. Moving down, less solid waste than paperboard. Okay, that's what I meant to say. Now, you can see here again the linear low-density polyethylene showing up as very low solid waste. And as was mentioned here from the experience in Argentina, that linear low-density polyethylene is also the cheapest. Right? Until you get out to 30 uses of high-density polyethylene, right, which is probably unlikely.
One quick question. So, just back on her point on the trip thing. For the 30 trips, so we're talking about transporting 1,000 gallons. So that means for 30 trips, they're around 33 gallons per trip. Is that?
No, it's basically you can think of it as you buy a gallon of milk in a glass container at your house. Use that gallon of milk. Bring it back to the store. The store then has an infrastructure to redeliver that empty container to the milk processing facility where that glass is cleaned, refilled, and then brought back to the store. Okay, and that's done until 1,000 gallons is consumed.
Liquid waste from washing bottles, essentially.
It was considered here, but we didn't actually measure up the aqueous waste. It was not a category here. It's a good point. The energy in the cleaning was considered.
Yeah.
Yeah, good point. Other questions? Okay. Wonderful. So they are, as much as we tried to come up with, equal use phase, right, we really don't have equal use phase. In terms of the customers that were surveyed during this investigation, the high-density polyethylene refillables and the high-density polyethylene single-use were the most preferable. They're able to block UV. They're not transparent. They are lightweight. They don't break if you drop them, etc. Right? We probably all dropped one of these before. Polycarbonate was good also. Excuse me. But they're less able to block UV. If anybody's seen polycarbonate container, we actually have one of these in our house. We use it to put cereal in. Now, for a while, we were using it for milk, but now we use it to store cereal. But it basically doesn't block UV, so that reduces the nutritional value of the contents inside the containers. The UV can break down vitamins. The pouch can puncture. It can be difficult to reseal. I don't know. I've never used one. But I would imagine it sounded like, as it was being described, unless you're actually used to it, right? It sounds like a little bit more work, right? And we may not be tolerant of that. And, of course, it has to be cleaned and stored, the pitcher that goes in. Glass had a low overall score due to its potential to break. It's heavy. Right? If you ever put a glass container in a paper sack and watch what happens, could be trouble. Paperboard, everybody's had difficulty opening one of these containers before. When I was a kid, I couldn't even do it. And I wasn't allowed to in the house, just because I would always, if you do it wrong, you rip it, and then it leaks everywhere. I was the kid that was notorious for doing that. So I was banned from opening milk containers. Probably still am. Of course, if you refill, you have to have an infrastructure to do that. And that goes to the example or the question that was asked in the back. Is there an infrastructure to do this, refilling infrastructure? How exactly are these 1,000 gallons being delivered, as was asked up front here? And how do you encourage returns? Right? If you have a deposit fee that's too high, then people aren't going to choose to buy milk that's delivered in that product delivery system. If it's too low, nobody's going to pay attention to it. Right? So, and to go even further with the point that was raised, if the cost of the packaging isn't showing up in the cost of the milk, then who cares whether a linear low-density polyethylene pouch is cheaper or not, right? Unless you understand maybe a little bit about the environmental issues. Right, so if we talk about design guidelines or principles of eco-design for milk packaging, right? We can minimize life cycle energy by minimizing production energy. And that becomes particularly important for single-use containers. If we're going to refillables, you have to have the infrastructure. And that infrastructure, of course, you'd want to minimize the life cycle impacts of that too, because as you get out to 30 trips and 30 refills, then you want to minimize empty container costs and energy consumption and the refilling process, the cleaning process, etc. Okay, probably obvious stuff here. The postscript here, and I think we've covered just about all of these. The linear low-density polyethylene flexible pouch had the lowest life cycle cost. So it turns out that the high-density polyethylene, the polycarbonate, the flexible pouch had the lowest cost. So this is a case, probably a rare case, where the environmental incentives and the economic incentives actually line up. But it's sort of like energy use in a factory also, right? If you can minimize your energy use, you're probably going to minimize your costs too. But if you're not concerned about those costs, or those costs aren't high, you may not pay attention to them. Right? Now, in the U.S., we talk about milk packaging and consumer perceptions. They tend to be driven by a single attribute. So ask consumers what is more environmentally preferable, a plastic high-density polyethylene 1-gallon container or a glass container. They're probably going to say glass. And that's what they found in this investigation. Because especially here in the U.S., we don't focus on life cycle. We focus on a single attribute. And one can be cynical and say that consumers can only understand one attribute at a time. Or we can say that, well, consumers haven't been educated to think life cycle one way or the other. I don't know which one's true. But consumers would tend to think that glass is more recyclable. And in actuality, about 1/3 of HDPE is recycled. Only about 1/5 of glass is recycled. And by the way, glass is a lot more material to begin with. Right? So the waste is a lot higher, and this cannot be seen as an environmentally preferable product delivery system for any reason. Right? So we need to become better aware, and actually we have moved away from glass as a packaging system here in the U.S. I don't know where it's being used more, if anywhere. But it boils down to ecometrics. Right? What are the appropriate metrics? And here's a case where you can pick some very simple metrics and come up with clear environmental decisions. Okay. Any questions on milk packaging? So we can move a little bit closer to design now, at least the types of decisions we might make in design and manufacturing. And this is a case study actually done here at the University of Michigan, led by Professor Keeley and Down School of Natural Resources and the Environment. A Ford Contour engine, 1995 model, investigating 3 different types of air intake manifolds, basically distributing the air to a 4-cylinder, 2-liter engine. We have a sand cast aluminum case here, a brazed aluminum tubular. This is a combination of secondary aluminum and primary aluminum that's sort of soldered together or brazed together. A nylon composite engine. Okay, here we have a material selection choice. What are the materials? Here on the, this is your left-hand side. We've got the nylon composite. Nylon composite is mostly nylon, but it actually needed a different EGR component. What does EGR stand for?
Exhaust gas.
Yeah, exhaust gas recirculation. Right? Hot gases, probably not the best combination with nylon, so they needed a stainless steel EGR tube to go with this. They also had some brass straps. What is brass? We didn't talk about brass.
Copper and tin.
No, copper and zinc.
Copper and zinc. Okay, mostly copper though. And you remember, what do we remember about copper and copper material production?
You can float it.
You can float it. It's also found in relatively dilute concentrations, and there's a lot of waste created in the processing of copper. Right? So stay tuned. We'll use that knowledge again here in a minute. Sand cast. This is secondary aluminum in the center. Okay, quite a bit higher mass here. Material isn't quite as strong, so one might not be surprised that the casting would have more material associated with it to make sure it can handle the pressures. The brazed aluminum tubular is a mixture of primary aluminum and secondary recycled. But I don't think I've used those terms before. What's the difference between primary and secondary aluminum? Just assumed everybody knew.
Recycled and non-recycled.
Okay, but what's the processing difference?
Like cast versus like hot rolled or this kind of stuff?
It actually goes a step further back in the processing. Right, in aluminum we had bauxite, again a mineral found in the Earth's crust, rather abundant, still relatively dilute, and we use this high pH precipitation process to get that aluminum out in a very highly pure alumina form, which we then used an electrolysis process to refine, making some CFCs and using a lot of electricity in the process. That was a primary aluminum. Virgin aluminum is how I referred to it as. Recycled aluminum is melted scrap aluminum. Right? Now, the strength characteristics are going to be quite different, and that's the key thing here. So if we go back to the graph now and we compare the center here with the secondary material, you're going to have more of it required. Now, if you're going to have in the critical places some tubes that are primary aluminum and just braze them together in a solid soldering process, you can think of it as. This is a joining process that basically fuses the secondary and primary aluminum together. You can get away with using less material. Okay? Okay, so we see most material in the sand casting with secondary aluminum. Nylon's the lightest. Brazed aluminum tubular is near that, so less material than the casting. Okay? And here is the life cycle comparison of the three systems. Here in gray is the aluminum sand cast. In the hollow bar is the brazed aluminum, and the composite here is the filled-in bar. So what we see in material production is that the multi-tube brazed consumes the most material, and that comes from the processing of the primary aluminum material. Okay, a lot of material used up in that process. Now, while copper generally will have more solid waste than primary aluminum, there's a lot less of it in the nylon manifold. Okay. The sand cast aluminum has very little material production of solid waste because it is a recycled material. Okay. However, in the manufacturing, and this goes back to the point that was raised in the back, right, the casting, and we didn't talk as much about casting this term, but sand casting has a lot of sand waste associated with it, toxic binders and metallic air emissions. Okay, so there is a significant amount of solid waste in the manufacturing stage with the sand casting. Less with the multi-tube brazed, because again, you can think of this as a solid sort of soldering joining process. The composite forming, still some material waste associated with that. Use phase, relatively little. This is only repair and warranty and replacement of the manifold, so relatively rare. Product retirement, you guessed it, nylon's not recyclable. We can recycle aluminum. So if we add up the solid waste over the life cycle in terms of kilograms, right, here is the relative comparison. The multi-tube brazed due to the primary aluminum production. Remember, the solid waste form was this red mud we briefly discussed on a slide way back when. Okay, that's in the primary aluminum. Most of the composite is due to the failure to recover the nylon material. Although nylon can be recycled, generally isn't. If we look at energy use in production, they're not very different from one another. The manufacturing stage, again, casting, you're melting a lot of energy and handling a lot of sand. So it's going to be relatively high in the casting. And here is the use phase, right? A familiar old story, right? The heavier, higher mass aluminum is going to drive the use phase. So this scales with weight. And therefore, what also scales with weight are the non-methane hydrocarbons, the NOx, emissions from the engine, carbon monoxide emissions, sulfur dioxide from fuel processing, nitrous oxide from the catalytic converter, and carbon dioxide from combustion. Will all follow the use phase. You see it dominating the other phase. Retirement, relatively little energy, regardless of what you do with it at the end of life. Okay, so here's the comparison. Following weight, as the familiar old story tells us. Okay, now the performance, were they all equal? They all met the basic requirements. I mean, Ford wouldn't go through the bother of doing a life cycle assessment on the three systems if they all didn't work, right? So they all met basic requirements, but still they were rated, and they had over 20 metrics of quality and performance, including manufacturability, durability, the airflow, right? The material, friction factor, how these materials are actually produced are going to affect how that air is getting into the engine, and in turn the combustion characteristics, performance of the engine. Dimensional stability, flammability, right? Nylon manifold, if it's close to a hot engine, might make you a little nervous. So flammability is for that nylon case. Noise, vibrations, lead times, how fast can you prototype it, all of these were considered. Generally, the aluminum cast manifold was ranked the highest. Nylon had some important advantages because quality considerations, fewer scrap instances in the production. The weight, of course, was important for CAFE standards, and the ability to integrate different components. Right, if you have a forming process and you have a design change, it's relatively easy in that forming process. Casting and brazing would be more difficult processes to change tooling for. So what would you do if you were Ford? Here's a life cycle cost. I know everybody's thinking about costs. Let's bring it out in the open. This is a comparison of a U.S. and German scenario. Okay, whether you're selling these in U.S. or Europe. The clear is the cost of Ford. The dark bar is the cost to the consumer in gasoline costs. And the end-of-life cost here shows up as credit is the word I'm looking for recycling. Okay, so you can make some money back. Assuming that the producer takes the material back, they can make some money on the recycle value of the material. Okay, so looking at, here's the, on the left, the cast aluminum, the brazed aluminum, and the nylon composite. So the cost of Ford is about $10 higher to go nylon. And that doesn't matter whether the product's being delivered to a U.S. or German market. Of course, the U.S. and German consumers are going to feel the pain of that choice much more. Right, here is the implications of a particular design on gasoline costs. And you can see here where the lighter nylon manifold is being used at much less cost to the consumer. Okay, so there's about if we just compare the cast aluminum and the nylon composite here, there's a $20 difference to the consumer over the lifetime. And whereas there's only a $10 difference to Ford. Right, so in our microeconomic utopia, it should be that we recover this rent, right? But it doesn't actually happen in practice. There's a disconnect here, and unfortunately, it's probably going to hurt the environment, right, in favor of cost to the manufacturer who's in control here. Unless the consumer really cared about that $20, right, which history has shown us that they don't. Here is the brazed aluminum tube, right? Just slightly more expensive to Ford, but some quality benefits there that may not show up in this cost. Okay, so what would you do? Right, anyone? Would you build the nylon if you were Ford? Everybody's shaking their head. No. Well, how about the environment? Probably wouldn't, right? Because it is a dog-eat-dog world, right? And the $10 you don't collect goes to your competitor. Question?
Well, if you're not Ford, if you're Ferrari, for example.
Say again?
If you're Ferrari, for example, and every ounce of weight counts, you will build an island.
Yeah. Okay. This is a Ford Contour. It's not a Ferrari. Don't you wish it were? We could all have a Ferrari. But yeah, that's an excellent point. The performance would really matter. Yeah, the whole game changes. And talk about aerospace. Let's say I'm going to save my remarks about aerospace because it came up, one of the term projects off campus is in the aerospace industry. And what I've been learning about the aerospace industry from some of our colleagues over there is that they tend to lag in terms of certain manufacturing techniques, lean manufacturing, and environmental considerations. So these are new ideas over there. But light weighting certainly isn't, especially in aircraft. Since the Wright brothers took off about 100 years ago, the light weighting has been known to be a critical issue. Another question.
I didn't understand that the nylon was better for the environment.
Well,
what you showed.
Well, here is energy consumption, right? And here is solid waste. Now, it's important to note that the sand cast aluminum, because of its recyclability, has less solid waste, right? But in principle, the nylon could be recovered. It just isn't, right? So if we cared really about the environment, we could get this black bar to be about the same if we recovered the energy, and the solid waste would drop way down, right? So it's a pretty clear choice here, although you're right, and this is an important point of confusion that should have been raised. On the surface, it might not be obvious, but we see that nylon, and this was a point I meant to raise, the nylon solid waste issue could be addressed through energy recovery, right? Further addressing the energy issue, and by the way, while we didn't quantify the air emissions, clearly it's shown in the energy use. They're going to be driven by the use phase, and we've seen this in a number of cases already. Okay. So maybe a little less obvious than I made it. Okay. Okay. So probably the sand cast aluminum tube is going to be the way to go. I believe that's what they did. But here's a postscript on the case study. Can you really do a full life cycle assessment on each design concept? Did we for the coffee maker? Remember our simple approach to eco-design. Right? We talked about understanding your product, understanding the life cycle, and then doing something about it. Step 1, step 2, step 3. But can you do a life cycle assessment for every concept? You can't. So to some degree, you have to borrow from other life cycle assessments and use your best judgment, trying to keep as much of the scope in common as you can. That's what you do as a designer. But at the end of the day, not everybody's going to take an ME 589 class or what have you, so we're not going to have environmental experts everywhere in design. So we need to boil these down into the metrics that are most important. And you can see here we're beginning to do that. We're not using eco-indicator points. We're not using EDIP, which I'll introduce on Friday, but we're using relevant emissions categories from life cycle inventories that, while they have some uncertainty associated with them, they're much less uncertainty. At least we can quantify the uncertainty, whereas in the impact stages, maybe we can't do so well. Things such as the amount of primary material in the finished part. For the manifold, it matters. Primary aluminum drove the environmental decision between the brazed aluminum and the sand cast aluminum. Use phase energy and carbon dioxide emissions, the solid waste at the end of life stage, carbon dioxide emissions. All of these are relatively easy to implement at the eco-design level. As you design this part in a computer-aided design environment, one could easily tabulate these metrics along the way. And that's the most common form of eco-design that we're beginning to see. Electronics industry is leading in that regard, but the automotive industry is beginning to catch up.
Help cut the time down from a year to actually do a life cycle analysis?
Yes. I mentioned before that the Japanese government has catalyzed a national life cycle assessment database. I haven't been able to see it. To my knowledge, still under construction. Maybe I'll learn more when I'm in Tokyo in about 3 weeks or so. But this is something that even with a concerted government effort, and it's a modest effort. It's not a huge effort that's going on over there in Japan. But certainly, as more data became available, you could get this down tremendously, get the cost way down. But again, it's life cycle cost because it would take society investing in a lot of research on these topics to produce that database in the first place. Would it average out to be 100K per LCA? Well, probably there would be a lot of efficiency there, and it would be less than it. But in the use phase of the LCA, where you have designers now utilizing that, the cost would be minimal, right? It gets into the things that only the assumptions and the modeling of the product itself become important. That's what designers are best at, right? But again, we're a long way from there. Other questions? Okay. Okay, so we've beaten this to death now, right? So you know that the material selection is not just about the material. Okay. Minimizing mining and processing impacts. Let's compare. This is from a life cycle assessment database. It was provided by what's called the BUWAL database. One of the Swiss ministries provided these data. Let's compare a kilogram of steel, aluminum, and ABS plastic, acrylonitrile butadiene styrene, used often in helmets and computer housings and the like. Okay, remember Eco Indicator 99? We've talked enough about it. Remember, this is relative damage in 3 different categories: human health, ecosystem quality, and resources, weighted together by our magic number of some subset of 45 practitioners, right, leading to this weighting over here, and we multiply it by 1,000, right, and we somehow got the average damage caused by a European per year in these 3 different impact categories, and we add them up. Right? That's the basic philosophy behind Eco Indicator 99. Where does Eco Indicator 99 come from? It starts with emissions, and emissions converted into human health impacts, resource utilization impacts, and megajoule surplus impacts. And just to show you what goes into these databases, and we did show this for the coffee maker already, here is for a kilogram of steel, aluminum, and ABS. The steel is in blue. The aluminum is in red, and in yellow here is ABS. Right. Nickel emissions to air and water, cadmium emissions to air and water, chromium emissions, polyaromatic hydrocarbons, benzene. This is formaldehyde. Acrolein is in here somewhere. Acetaldehyde, benzene, to water dioxin, etc., etc. You have to tabulate all of these in terms of emissions and convert them into disability-adjusted life years. This is for carcinogens. All of these are known carcinogens. It's a log scale, so basically nickel and arsenic are going to drive this. Here are respiratory organics, also contributors to human health damage. Non-methane volatile organic compounds, methane, pentane, xylene. All these are organics. Right? Carbons, usually hydrocarbons, often containing oxygen. Right? If we see over here some of the major ones, these are general hydrocarbons, linear or branched linear. We've got aromatic hydrocarbons over here on the plastic side, really driving this. But what's interesting is that the plastics has less diversity in terms of the impacts, but the magnitudes are still significant. You see steel and aluminum are showing up in many different categories, but plastics, fewer categories, but nevertheless still some very strong impacts, especially when we think about this on a log scale. Question?
So where's the formaldehyde coming in from the steel?
Good question. I don't actually know. Could be fuel that's used in the coke process, and I'm just guessing here. But to purify solid carbon fuel from coal, you're going to make various hydrocarbons. That's a high-pressure, high-temperature process that's going to yield a wide variety of hydrocarbons. And that would include formaldehyde process there, especially if you have poorly combusted products in that coal process, that coke burning process to make the steel. Pretty good opportunity for formaldehyde production there. Could be other sources, just wouldn't come to my mind straight away. Right, so you get away from this. Right? That's a danger here, right? Where do you ask really good questions, right? You can investigate where does formaldehyde come from. It turns out formaldehyde is relatively low in terms of the DALYS here, so that might not be the one you want to hunt down. But at least you're smart enough to know where steel and aluminum and ABS comes from, and you know, okay, if it's plastics, go into the petroleum industry. If it's steel, you know a little bit about steel production, how that's made, where to ask the questions. Is this really important, or is the place where I get my steel from, maybe they're using a direct reduction process. Maybe they're not using coke at all, right? And formaldehyde doesn't exist. I mean, these are the questions. This is exactly the type of question that you should be asking when you apply these life cycle assessment databases. Are they really relevant? Is the scope really the same? Is the data old? Have processes evolved? Are emissions controls now in place where they didn't exist before? These are hugely relevant questions that are often cast aside by the convenience of just using these data. Right? So hopefully we are stressing the difficulties that remain, even when we have such convenient types of forms available to us. Right? Remember, a little knowledge and an opinion, right, can be a very dangerous thing. Right? If I'm trying to demonstrate something and these data back it up, I may not ask. I may not bother to ask if the scope of these data are very relevant, if the primary impacts driving the disability-adjusted life years are really important. Right? So you have to ask these questions when your conclusions are being used to make serious decisions. Okay. In class, example problems, we probably don't ask you to ask those questions, but I would encourage you to do so. If you see an exam question, it's got something about formaldehyde there, you might want to ask. Maybe I'm using direct reduction plastic. I'm basically sticking scrap plastic into my steel refining process, and there's no coke there at all. Therefore, my answer to this problem is 0. How could I say that's a wrong answer? I would be, in fact, impressed. Right? So hopefully we're stressing that. Right? And it is exactly the reason why we spent so much time up front talking about where materials come from and what the environmental impacts are from manufacturing, et cetera. Okay. We can go through. We can do the same thing for respiratory inorganics. My only point here is to get you thinking, okay, what's a respiratory organic? Okay, that would be xylene, could be formaldehyde, could be hydrocarbons. What are my respiratory inorganics? These are dust, small particulate matter, sulfur oxides, NOx, sulfur oxides, etc. Climate change and ozone depletion, right? We know what those are. Carbon dioxide, we've talked about CFCs, and halons, right? Very familiar to you. And we don't have to talk anymore about these because we spent a lot of time already talking about these. So you can ask intelligent questions regarding them. So if we add up all the disability-adjusted life years for all the categories, basically we see NOx and carbon dioxide driving things, sulfur dioxide driving things. These were mostly respiratory inorganics and climate change, okay, by the daily point system. Right? We could go through a similar argument. You know how I feel about the ecosystem quality. We could do the same for megajoule surplus, mostly from resource consumption, right? Crude oil, natural gas, coal, and bauxite. No real surprise. Iron is relatively low. As you already know, iron is relatively abundant. Right? Okay, so we can summarize our impacts. And these are relative impacts. These are the human health categories. So here's carcinogens, respiratory organics, respiratory inorganics. This is relative impact on a millipoint scale, eco indicator 99. Blue is aluminum, green is steel, and red is plastic, ABS. So this is kilogram, kilogram, and kilogram. So here's a kilogram of aluminum. You see a lot of blue up here at 100. That means aluminum had the most, and the steel and plastic within that category are normalized to it. Okay, plastic dominates in respiratory organics, as was pointed out, and steel dominates in ecotoxicity, red flag, and that's it for steel. Okay, so we can do a relative damage assessment, but here's where it basically shakes out in the eco indicator 99. Kilogram of steel has the least amount of eco indicator 99 score. Aluminum has the most, and ABS has an in-between amount. Mostly driven by resources and human health impacts. Okay. Whereas the difference between steel and ABS is in resources. So then you have to start asking some questions, right? What questions do you have? So this means steel is the most environmentally friendly, right?
Are the human, ecological, and resources at the 40-40-20 distribution?
Yes. In this case, they are. Yeah. So steel is the most environmentally friendly, right?
Well, according to those distributions.
Okay, so it is.
Well, the comparison based on weight, right?
Yes.
When you construct something, it's the dimensions that count, essentially.
Yeah. Point number one, how much are you using? Right? Hard to isolate that. We've said that a number of times. Now, what else?
Does this take into account the energy you'd need to process it into different shapes?
No, manufacturing is not accounted for here. This is only up to the material production stage, as it might commonly be delivered to a manufacturing facility. Billets, rounds, plastic pellets, etc. Yeah, I mean, the ABS may be quite strong, right?
And light.
But?
And light.
And light, yes, absolutely. Are we recycling them? Right? Maybe the steel you're using is recycled, or the aluminum you're using is recycled. Right? What are you doing at the end of life? Right? All these are questions. What if the metrics are weighted differently? That was a point raised here in the front. Right? So, I mean, you're asking exactly the right questions. You can't just use these data in isolation. Oh, and by the way, is this the only way to rate the materials? We didn't actually add up the inventory numbers. Right? It gets a little bit complicated, but we could have made that study also. Question?
It didn't have a use phase, right?
No. Not at all.
Depending on the application, if this was a boat or something, a steel boat's going to rust in a couple of years. By an ABS boat's going to last,
yeah,
50, 100 years.
We're rather auto-centric, but boats are out there too, and so are planes, right? We haven't talked much about buildings this term. That's something else. And actually, these are, if we talk about term projects, things were in 589 when it's taught in the fall of 2004, we will be talking about, thanks to the contributions that are going to be made by some of the term projects here. Okay, so these are all great points. Recycled versus non-recycled steel. Blue is virgin steel. The recycled steel is in green. The recycling process can be polluting, especially with respect to respiratory, inorganics, and climate change, but on the whole, those are normalized numbers. You see that the resource consumption is a lot less, and that's what you would expect, right, in an Eco-Indicator 99 approach. Aluminum, if we look at recycled aluminum versus virgin aluminum, right, it's quite obvious. Recycled aluminum, secondary aluminum, has less environmental impact by this weighting system, right? But I want you to think hard about the difference between using Eco-Indicator 99 points and inventory categories. Inventory categories have the disadvantage of lumping things together. For instance, I might talk about kilograms of air emissions, right? That says that an air emission of carbon dioxide, NOx, is the same thing, and we know that's not true, right? So that's a weakness there. But the numbers are a lot less fuzzy. Whereas if we include the impacts, right, now we are talking about things on an individual basis, but the uncertainties are huge. So using many different point systems, right, and trying to do both, really getting into the numbers, asking questions about where the data came from. Where is that formaldehyde coming from? And is that really driving the decision here? You have to do that when you're not making back-of-the-envelope calculations. Okay. Paper sacks versus plastic sacks, right? The age-old paper versus plastic. Now, if you use Eco-Indicator 99 just to make the sacks, right, and this actually accounts for the manufacturing process, which is another question that was asked. You see, it's probably a wash. Right? They're not very different in terms of the errors embodied here. Right? So how many people think plastic's more environmentally preferable? A couple. Paper. A couple. How many? Three, maybe. Within error. How many people don't know? All right, so why don't you know? We haven't done our job in this class. We're defeated.
There's not biodegradable plastic bag.
Not in this case.
Yeah.
Cloth?
It's not an option here. We got two choices. Yeah, cloth would be good if you use them. Some people just buy them and use them once. Do we have another comment?
I don't know, I'm just kind of thinking about use phase.
Yeah, of course, right? It's just like the diaper example, right? How do you use it matters. If you recover your plastic bags, a lot of places will take these back right, and use them as a recycling process to make new bags. A lot of people use them as trash bags, right? Get away from using these dual or tri-ply hefty bags in their kitchen, right? Why can't you use these bags, right? That's what we do in our house, right? It's cheaper too. So, you know, it all gets down to how you use it. And the point here is that the materials are pretty close, and it's actually irrelevant, right? It all boils down to what you do with it, right? So that's why the age-old question will continue. Well, minimizing material amounts, this is something we've talked about before. You know, less weight, less to transport, especially in a product such as an automobile. We talked about it in a cell phone housing, right? Minimizing material by minimizing the over-dimensioning, right? Rigid by geometry, not by over-tolerancing, right? That's one way to achieve using less material, right? Or choosing different materials. You can actually use less material. We talked about that in milk packaging too, right? In a transportation product, just to really beat your heads with this point more, all right? If you can increase if we talk about minimizing materials, we could talk about minimizing gas consumption, right? Gasoline's a material. 20% increase in fuel efficiency, right? Reduces the amount of fuel that's produced by 20%, the amount of fuel transported by 20%, solvent vapors and potential leaking at filling stations by 20%. The mass of the vehicle goes down because of the structure. You have less need for a strong fuel tank, so the fuel tank can be a little bit smaller, maybe a little bit weaker, depending on how much structure you need to support it. Right, so you got a lot of positive feedback loops, right? So you could say, well, how much material, if I talk about gasoline, this is a comparison of gasoline. 20% fuel efficiency increase leads to 20% environmental emissions reduction, right, an eco indicator. Right? But there are a lot of other positive feedback loops that also need to be considered. Right? So I think by example, you're beginning to get the right way how to think about these things. Right? And it's hard to give homework examples, really, in this way. Right? I mean, I could ask you to design something, projects, and really in the term projects is where you're applying this stuff. Right? Manufacturing impact, we're going to talk a lot about Friday. Interesting example was brought to my attention just a week or so ago. Right? What if one were, instead of trucking shipments of goods up and down the East Coast, one just were using ferries or ships, right? Loading tankers, or if you will, I don't know, what are they, container ships, right? That's what they're called, right? Of material, and using that form to take goods from Boston to, I don't know, what's now on the coast? Savannah? Is Savannah on the coast? Or, yeah, okay. Up and down, right? Would that actually lead to less environmental impact? This study has been done. It suggests that there may be less environmental impact associated with that form of transportation. Of course, you'd have to ask questions about jobs. Actually, economically, could work out also. What happens to the truckers, right? How many people does it take to crew a container ship versus driving all these trucks up and down? Right? Questions you would have to ask. But we've talked about transportation and the urgency of transportation. These are eco-indicator points, millipoints per ton per kilometer, right? The further you send it, the more impact, the greater the mass you send, the more impact. Intercontinental air travel dominates here, right? And I couldn't resist. Any excuse to load up my flight simulator is a good one. So yes, I am at the controls of this particular simulation. This is a FedEx plane taking off from Willow Run. You're looking, and by the way, don't try to take off an MD-11 from Willow Run. The runway is too short, and you can barely get this thing off the ground. Anyway, yeah, you can see here everything that goes into intercontinental travel, right? A big bird here, a big heavy bird, and its volume is a lot less than a container ship, right? We learned this in the milk case study, right? The more efficiency you have, actually in the diaper study too, that the more things you can send together, the more efficient it is, right? The larger the packaging that you're delivering. the less environmental impact that you see, right? So would this really be an effective way, or an environmentally efficient way, let me say, to send material? Probably not, right? Most of what you're looking at is engine. Right? So think about what goes into the next FedEx package that you send, right? And who might be piloting the plane? That might be even more frightening. By the way, I didn't land this one. It takes about a half an hour. Sometimes when I'm really burned out, I'll just fire this thing up and try to take off a plane from Willow Run and stick it into a landing pattern to land at Detroit Metro. It's good fun. You're actually looking in the back here at Lake Sinclair. So that a lot of the scenery is realistic. But we actually have to take intercontinental air travel out of this to make other comparisons, right, between container ship here, rail, and truck. You can either have a small truck or a large truck, 16-ton truck, 40-ton truck, or a sea transport in general, so bigger container ship essentially. Right? And we see basically what we see. Larger volumes, the more you can take together, right, on a single trip, the more efficiency. Okay, 16-ton truck isn't going to be as efficient as a 40-ton truck. And a small plane isn't going to be as efficient as a big plane. Okay, so your intuition is functioning well. Okay, in-use impact, right? One more case study for us before we move into manufacturing on Friday. Here is fuel tank example. Producing a fuel tank out of high-density polyethylene versus steel. Now, in this case, this was a GM full-size van. Case study for the fuel tanks. We got a 31-gallon steel tank and a 34.5-gallon high-density polyethylene tank that's normalized now to 31 gallons. Lifetime of 110,000 miles is considered here. And again, the scope has to consider the system components implied by the material choice. For instance, steel tanks require a plastic shielding to protect from humidity and salt and stones. Right? Stones can crack the fuel tank, salt can corrode it, etc. It's interesting that a steel tank requires some plastic and a plastic tank requires some steel. The steel in the plastic tank case serves as a heat shield. Okay? So there are other materials implied by the choice of the fuel tank. And when you break it on down, this is the plastic tank. In blue here, this is the high-density polyethylene. It's a multi-layer fuel tank. You've got PVC-coated steel straps and a steel shield. Okay? This is mass. And you've got a 14-kilogram mass on the plastic tank. The steel tank has about 17, maybe 18 kilograms of steel, about a kilogram of painted steel straps, and a high-density polyethylene shield. Note that the mass of the shield is higher, even though it's plastic, for the case of the steel tank than the plastic tank, because they're serving different functions. Right? Steel, obviously, is stronger. You can get away with using less of it. Plastic, if you're going to use it as a mechanical barrier, you're going to need more of it. The life cycles of both fuel tanks are similar. Right? So steel, we talk about the production of steel, coke, limestone, iron ore. In the plastic case, you've got natural gas and crude oil, all working into the vehicle assembly, bringing the straps, the shield, and the tank together into a use phase, dismantling phase, etc. If we look at the life cycle energy in gigajoules per tank, we see that the steel tank leads to a lifetime fuel consumption of, well, let's say about 25,390 liters of gasoline, of which 57 is attributed by mass to the tank. So we look at how much fuel is consumed over the life cycle of the van. We divide it in terms of a mass ratio by the ratio of the tank to the ratio of the vehicle. If we use the high-density polyethylene tank, we use less gas. Right? And the 57 and the 88 are reversed here. So the steel tank uses 31 liters more of gasoline than the high-density polyethylene. Okay, typo there. Okay, so looking at the life cycle, here is gigajoules per tank. Material production is not very different. Manufacturing isn't very different. Of course, the use phase is dominating here. End of life doesn't really show up. Old story. Solid waste, much more in the steel production than the high-density polyethylene. Manufacturing, more waste in the high-density polyethylene case. Use phase, failure is rare. Repair, maintenance, warranty is rare. End of life, certainly you're going to have much more solid waste in the high-density polyethylene system, especially here in the U.S., as this fuel tank's unlikely to make it back into the recycled stream. Okay, steel stream makes some waste, but not as much. So on the whole, it's roughly a wash. Okay. So what would you conclude? If the solid waste is roughly a wash, the energy, of course, we know, again, it's transportation products really driving things. Air emissions are going to follow. Did we talk about water wastes? No, we didn't. So you have to ask. This would be one of those sort of intelligent questions that you'd ask. What about water? If I choose the plastic tank, would there be more water waste? Okay. But otherwise, things are following exactly the same sort of logic. Same with the coffee maker. Use phase is driving it, right? So you're beginning to hear an old story. And we asked earlier in the term, right, is manufacturing environmentally important? All of these cases we talk about, use phase is driving. All right, and we're going to begin with that question on Friday. Is manufacturing important? Okay, so we'll see everybody then.